Very good afternoon, ladies and gentlemen. So we are back with the inaugural lecture series, which is brought forward to you by the Faculty of Graduate Studies. So on behalf of the Faculty of Graduate Studies, let me warmly welcome all of you for the 45th iteration of the inaugural lecture series. So inaugural lecture series always has been interesting because it always enlightens us on something new, be it theoretical or practical. We'll be always learning something new, and at the end of the day we'll be taking something home and we'll be pondering on something that the professor of the day would be teaching us. So I'm pretty sure the day today would be also very similar. We'll be learning something new, we'll be taking something back home too. So without further ado, let's move into the proceedings of the day. So it's all about the first and foremost, it is time to introduce the professor for the day. So for that, I would now like to invite Professor Buddhika Jayasekara, Head Department of Electrical Engineering, to introduce our professor for the day, Professor W.D. Prasad, once again from the Electrical Engineering Department.
Good afternoon. Professor Prasad received his BSc Engineering degree in Electrical Engineering from the University of Rotor in 2005 and his MPhil in Electrical Engineering from the same university in 2007. After serving as a probationary lecturer in the Department of Electrical and Information Engineering at University of Ruhuna for 1 year, he joined the Department of Electrical Engineering, University of Rotor in January 2009. In September 2010, Professor Prasad joined the Department of Electrical and Computer Engineering at University of Manitoba, Canada as a research assistant to pursue his doctoral studies. During his PhD, he was awarded prestigious University of Manitoba Graduate Fellowship and MICAS research grants. His doctoral dissertation was on novel algorithms for rotor angle security assessment in power systems. He completed his PhD and resumed his academic duties at University of Rotor in November 2014. Professor Prasad was promoted to Senior Lecturer Grade 2 in February 2016 and Senior Lecturer Grade 1 in January 2020. In recognition of his academic and research achievements, he was promoted to Professor in Electrical Engineering on merit in November 2024. Throughout his academic career, Professor Prasad has contributed to the Department of Electrical Engineering and University of Rotor in various academic, administrative, and professional capabilities. He is also a senior member of the IEEE. His research interests include power system modeling and simulation, synchropressor applications, and real-time monitoring and assessment, control of power system stability. He has contributed to international research activities through CIGRE, International Council on Large Electric Systems, working groups on applications of pressure measurement units for monitoring power system dynamic performance and review of advancements in synchropressor measurement technology. Professor Prasad has been recognized for his research excellence through Outstanding Research Performance Awards from the University of Rotor in 2018, 19, 21, 23, and 24. In 2021, he was also honored with prestigious presidential awards for scientific research in recognition of his research contributions. Over to you, Professor.
Right. So good afternoon. Thank you, Professor Gopura, for giving me this opportunity. And thank you, Professor Buddhika, for your nice introduction about myself. And I warmly welcome all of you, those who are physically here and those who are joining online for my inaugural lecture. So to begin this inaugural lecture, I would first like to have a question like, what happens in few seconds in a power system after a major disturbance? Maybe a tripping of a transmission line or an outage of a large generator. So the question in mind is whether we get power or not, or in technical terms, whether we will be stable or not. So that's the journey that I would like to take you through today during my inaugural lecture, which is on from swing equations to artificial intelligence, the evolution of rotor angle stability assessment. So this talk is organized under 4 main sections. And first, let's have an introduction to the rotor angle stability problem in power systems. So to begin my talk, let's first have a look at an interesting video. Right. So here we see a group of dancers. They are dancing to a rhythm and they all are maintaining good timing also. So they are synchronized with each other and with the rhythm. And let's see how this is applicable to a power system. In a power system, we do have different elements, a group of generators connecting to the network, and they generate power. And the generated power is transmitting through transformers, transmission lines, and distribution network, and then reach the load centers. So in steady state, there is a balance between the power generated by these generators and the load demand. So we say that the system is operating in an equilibrium point. At this condition, all the generators connected to the network are approximately rotating at their synchronous speed. So a synchronized system is not something that doesn't move. It is something that everything move in a coordinated manner. So with respect to a power system, we can say a synchronized power system is an interconnected network in which all synchronous generators rotate together at a common electrical frequency while maintaining stable phase angle relationship. Now let's imagine one of the dancers in this particular group lose synchronism or rotate in other way around. Then the entire group may start losing synchronism. So that's the same thing that can happen in a power system subjected to a disturbance. So let's assume a scenario where there is a fault in one of these transmission lines in this particular network, and the line is stripped. So let's see what's going to happen. And if we do a simulation for this kind of a scenario, we can see that the rotor speed, or the speed of the generator, is deviating from the synchronous speed, and that's what you can see in this particular 4 graphs. So this is showing the rotor speed deviation with respect to the synchronous speed in the previous power system. So in this particular case, all the rotor speeds are decaying with time, and they are settling to another equilibrium point. So in this case, we say that the system comes to an equilibrium point after the disturbance, whereas all the state trajectories are bounded. So that gives the idea of the definition for the power system stability. So power system stability is the ability of an electrical power system for a given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance with most system variables bounded, so that practically the entire system remains intact. So you can see there are 4 key terms which are highlighted, because initially a power system is operating in an equilibrium point, and then it can experience different disturbances. After these disturbances, if the system can survive with all these trajectories bounded, we say that the system is operating in an is coming to a stable condition. And now in the previous scenario, I showed you like the variation of the rotor speed compared to the synchronous speed. And we say such oscillations are electromechanical oscillations. And any idea about the frequency of that oscillation? That's like a small frequency, that oscillation is a low frequency oscillation where their frequencies are usually lesser than 2 Hertz. Now, in real situations, we do not see such oscillations. What we see is the generator speed accelerates and decelerates. So how it is appearing in actual system variables? Now, in this case, what I am showing here is the stator current variation of the Lakvijay power plant unit 1 subsequent to a failure in unit 3. So you can clearly see that in steady state, the rotor current is varying at 50 Hertz component, or it's at the fundamental frequency, it's a sinusoidal waveform. And that sinusoidal waveform itself has a magnitude and a phase angle. And let's assume because of the disturbance, we get 1 Hertz additional frequency component on the network. So the 50 Hertz waveform is amplitude and phase angle modulated by that 1 Hertz additional frequency component. So if we do a frequency spectrum analysis, we will see 51 Hertz and 49 Hertz frequency components. And we see this additional frequency component as an envelope, as you see here. So when it comes to rotor angle stability assessment, our interest is on stability analyzing the stability of these low frequency oscillations. Now, in this case, that oscillation decayed with time and the system settled. And let's see what happens if this oscillation diverges. Now, in real situations, we know there are adequate protection in these generators. So if the speed is identified to be going out, then there are protection to act, and they will be activated and the generators will be tripped. So I do not have real physical waveforms to highlight this scenario, rather a simulation case. And I'm showing here two graphs where you can see rotor angle versus time under two different cases coming out of the simulations of the 16 generator system without adequately modeling the relevant protection schemes. So speed is the rate of change of rotor angle. So the same information will be visible in the speed also. So in the first scenario, you will see the angle increases indefinitely in the first swing, which is known as first swing transient unstable scenario. Whereas in the second scenario, in the first swing, it turns back. And then in the second swing, also it turns back. And from that onwards, it is rising. So which is known as multi-swing transient instability scenario. So when it comes to transient stability assessment in power systems, this is the major concern to identify whether the system is having sufficient synchronizing torque and whether it can survive from the disturbance. In real situations, now a disturbance can trigger to number of cascading events, and the system can come into a total failure. So I have two cases. Now the first case here is 2016 event in our power system 10 years ago, but you can see that the system collapse has initiated from one of the line to ground fault in Kolonnava Sitaka 132 kV line, and it has triggered cascading failures, and eventually the system led into a total outage. And the second scenario is the famous that monkey event which happened in last year. So because of that situation, one of the transformers in this Mandra grid substation failed, and which triggered cascading events. And we can clearly see that number of generator units went out from the system due to frequency issues. So the two things that I want to highlight from in this slide are that a single fault can trigger number of cascading events unless you take control actions on time, and also look at the time of interest in this particular domain of analysis. It's in the seconds. So when it comes to transient stability assessment in power systems, we have to take actions as quickly as possible to secure at least part of a power system. And so here, this is a classification about the power system stability, and we can see different forms of, there are different, basically two major layers. Let's say rotor angle, frequency, or voltage. Those are the main variables in which we see the instability. And then transient or small disturbance is the type of the disturbance. The transient or large magnitude disturbances are like three-phase short circuit faults, where their effect to the network is severe, and you have to consider nonlinear dynamics of the system when it comes to analysis. But if it is a small disturbance, the magnitude of the disturbance is considered to be relatively smaller, so that we can go ahead with the linearized models. And with the interconnection of these non-conventional wind and solar into the grid, the new power system stability classification has two more stability issues, which are shown as resonance stability and converter-driven stability. And the focus of our topic today is to discuss about the rotor angle stability. So why a rotor angle? What is the importance of rotor angle stability? Now, in steady state, as we discussed, all the synchronous generators connected to the system are running nearly at the same electrical speed, but that does not mean that they occupy the same rotor position. Each generator occupies its own rotor angle, and that angle difference creates the active power flow through the transmission lines. subsequent disturbances, the resulting oscillations decay with time, and if so, we can say we are stable. Otherwise, these oscillations can grow in the first swing or multi-swing, resulting in the instability of the system, and which can lead to number of consequences as I have listed here. So it may be different issues which can give rise to, at the end, a total failure of the network. Now let's come to just one slide regarding the mathematics behind this scenario. So in this slide, you can see a synchronous generator is connected to a turbine, and the turbine is driven, maybe it's a hydro turbine or a steam turbine. So whatever the source is rotating the turbine, and then it produces this mechanical torque Tm, where the rotor of the synchronous generator is coupled with the turbine. So the rotor winding is fed by external DC source, and the resulting magnetic field is now rotating in the air gap, because the rotor is now driven by the prime mover, and that magnetic field interacts with the stator winding, and we will get a stable, balanced three-phase voltage supply in the stator side. Now, in steady state, this input Tm and output Te are in equilibrium, so we are in the steady state. What happens during a disturbance? Then there is a mismatch between Tm and Te, so the behavior of the rotor can be represented by based on the laws for angular motion. So this is the resultant torque is equal to moment of inertia times the angular acceleration, and then we define an important parameter in power system stability, which is the inertia constant h, which is given here. So which is the ratio between the total kinetic energy of the synchronous generator stored at the rated speed and the MVA rating of the machine. So larger the inertia constant, it needs more energy for speed to change, and therefore less acceleration or the deceleration of the generator. And with simple modifications to this particular equation, we can come to this second order differential equation, which is what is known as swing equation in power system stability, which is associated with the synchronous generator rotor dynamics. And again, we can also represent this second order equation as two first order equations, which gives us two state variables, delta, which is the rotor angle, and delta omega, which is the speed deviation of the machine. So when it comes to rotor angle stability assessment in power systems, our main focus is to deal with this particular equation or the two first order differential equations. To highlight this one, I have taken here a small example where a single generator is connected to a strong bus through a transformer and two transmission lines. And let's consider a case where a fault in second transmission line at the middle, three-phase to ground fault, and the protection activates and the line is stripped. So when we simulate the system subsequent to this disturbance, that means we solve the two differential equations that I showed in the previous slide, we can get the state, the trajectories of the state variables. So you see this variation, the first one is for the rotor angle and the second one is for the speed deviation. And these oscillations are now adequately damped and the system is in an equilibrium point. In theory, there is another way of representing this one, that's the equal area criterion. So we can simply get the power versus angle relationship of this particular situation during before the fault, during the fault, and after the fault. And we can show that if it can maintain the relationship, or in other words, if the area A1 equals to area A2, we say that the system is stable. So the physics behind this one is, during area A1, the generator gains energy. So that is in acceleration. And during A2 area, it releases the energy back to the network. So the system remains in synchronism if the generator can release the amount of energy that it gains during the period of acceleration. So that's the physics behind this one. So this is the simplest way of solving this particular problem. But you can clearly understand that when it comes to a multi-machine power system, this simple modification may not be directly applied. But still, this equal area criterion can also be applied to a multi-machine power system with some modifications. But we need some sophisticated methods. So in literature, there are plenty of methods. The conventional approach is that we can represent the entire multi-machine power system as a set of first-order differential and algebraic equations, and we can solve those nonlinear equations using numerical integration and get the state trajectories. And as long as these trajectories are converging, we say that the system is coming to an equilibrium position after the disturbance. So that is a so-called time domain simulation. And similarly, we have equal area criterion and its extensions. And also there are famous methods, the direct methods. In these methods, what we do is that we have a function for the energy of the synchronous generator, and we can calculate the energy at the time of clearing the fault. And if the amount of energy at the time of clearing the fault is lesser than the critical energy, we say that the system is stable. So those are the direct methods. And there are different direct methods depending on the way that we use to calculate the critical energy in the system. And I have specifically highlighted here another method, the method of Lyapunov exponents, which is completely a nonlinear method. Why I highlighted this was that it's one of my contributions during my doctoral studies to come up with new measure to estimate the transient stability status of the power system fast enough. So we can see it later. Right, now the system is stable after the disturbance. So you see set of decaying oscillations in the network. Then we come to the problem of oscillatory stability, whether the system oscillations have adequate damping. That's the main issue when it comes to oscillatory stability assessment. So we need to determine whether what are the oscillations present in the network and whether they have enough damping. So this is a case study for a 16 generator system where you can see the power flow through one of the tie lines is varying in the nature that I am showing in the graph. So we have to process it and identify whether the system has adequate damping or not. So here I added this slide, which an older an event happened in 30 years ago, but still that opened the eyes of the researchers also regarding the oscillatory stability of the power system. So if you look at this graph carefully, this shows the active power flow through one of the transmission lines. After a disturbance, the system settled down. We have decaying oscillations. So the system is now entering into an n-1 contingency scenario. And there was a second disturbance. And after that disturbance, the system went into oscillatory instability. So that's the importance of this particular curve, that system can lose the stability even if it settles down after the first disturbance. If the system has oscillatory modes which do not have adequate damping, a cascading event can bring the system into oscillatory instability. So similar situations were observed even in the last year. The famous the blackout happened in Portugal and Spain. One of the main reasons behind that incident was inadequate damping of system oscillations. So this highlights the importance of oscillatory stability assessment. So how we analyze oscillatory stability in a power system? To do that one, we go ahead with the model-based approach. That means we take the linearized model of the power system and we calculate the eigenvalues. Eigenvalues are poles of the system. So definitely, when we are operating in a stable equilibrium point, all the eigenvalues must lie on the left-hand side of the complex plane. Otherwise, you cannot come to the equilibrium position. Now, when we are in complex plane, the complex conjugate eigenvalues represents the oscillatory modes. So main idea here is to determine the state matrix, calculate the eigenvalues, and determine the frequencies and the damping ratios of these eigenvalues. And from that, we can determine what are the critical eigenvalues or what are the oscillatory modes which are vulnerable to other cascading events. So if they happen, these eigenvalues can jump into the right-hand side of the complex plane, resulting in oscillatory instability in the network. So this is the traditional approach of determining the oscillatory stability assessment in power systems. And we know but this traditional approach may not be suitable sometime when the system is getting, scale of the system is getting larger and larger. So there are different measurement-based techniques. So in this case, what we do is we capture the waveform and we process the data over a data window using signal processing and determine the frequencies of the oscillatory modes and their dampings and determine whether the system is having adequate oscillatory stability status. So now this is the basic behind the rotor angle stability problem, because our main idea here is to apply artificial intelligence into rotor angle stability assessment in power systems. But AI is that something we can apply, but unless we have a good understanding about the physics and the theory of and the fundamentals about this problem, you may not be able to get a good output even if we apply artificial intelligence into power systems. And that's why I gave kind of an introduction to the particular problem. So let's see now why we need AI kind of things in power systems. Now we know the power systems, the structure of the system is getting complex and complex. So many renewables are getting added to the network and the power system dynamics are completely changing. So the requirement is that if something happens in the network, because how well you design the system, you cannot avoid disturbances. They can happen at any time. So once a disturbance happens in the network, the idea should be to predict what will happen in future as early as possible and take the corrective actions. So that's where the need of AI when it comes to power system stability assessment. So we need the system measurements and we apply artificial intelligence with careful consideration to get fast adaptive decisions and or maybe to initiate required control actions. So how we can apply now? When AI is there, you are going to apply into a real power system. So what we need? Now, to apply this artificial intelligence, we need enough data. So, and those data should be capable of capturing the system dynamics. And if you remember the time scale associated with this, it's in milliseconds or seconds to scale. So we have to have enough data which carry useful information about the power system during the transient period. So can we do that with conventional SCADA data we have in systems? So this SCADA data, they refresh in maybe a couple of seconds, but that with that resolution, we may not be able to capture the power system dynamics. So the solution in today's power systems is to go for phasor measurement units, which provide synchronized measurements. So these devices, like they communicate with satellites and they provide time synchronized synchrophasor measurements. And those data, their sampling rate is depending on how we do the settings. For a 50 Hertz network, even it can provide 50 samples per second. So that means in terms of the technology, it's amount of big data. So with the help of this technology, you get big data into the system control center and they are time synchronized. They provide fundamental phases of voltage magnitudes and currents together with their angles, frequencies, rate of change of frequencies, complete observability. So many information are available in the control center with the help of this data. So this is how this shows how a synchrophasor network looks like. We can place the devices called PMUs, the phasor measurement units, in places which are important. So placing the PMUs to have complete observability in the network is an optimization problem. So from that device, you get fundamental phases of voltage and current, magnitudes and their angles to the central location, fast enough data. So we can employ any monitoring or processing algorithm at the system control center to process the data we get and initiate the control actions required. So what are the requirements then? So if my application is transient stability prediction, so I need the fast enough data, maybe which are available through the PMUs. and they provide real-time data. So when the data comes to the center, we may have missing data or bad data outliers. So we have to have data pre-processing, and then now these devices continuously send data. So the transient stability prediction will come into play only when there is a disturbance. So we have to detect that a disturbance has happened in the network, and then the selected data we have to process, and we have to determine whether the system is stable or not. So when it comes to transient stability prediction, the output of the algorithm is 1-0 kind of answer, whether yes or no. And even if you really need, we can further modify it to give the number of generators which are unstable, which generator, the stability margin, depending on how complex your algorithm is. If it is oscillatory stability assessment, we process this data to get the damping ratio. That's a key parameter when it comes to oscillatory stability assessment in power systems. So in a nutshell, when we want to apply the artificial intelligence into power systems rotor angle stability monitoring, we have to have enough data, and we process those data to get the stability decision and initiate the corrective actions. Now, if I show here, now this is an illustration for a transient stability prediction algorithm with the help of artificial intelligence and the data coming from phasor measurement units. So we first have a database. So in reality, to train let's say I go ahead with the supervised learning approach. So I need to train a classifier. To train the classifier, I must have enough data. But we may not be having real data to train a classifier such that it can capture all the system dynamics. So what we usually do is that we correctly simulate the power system in a simulation software under multiple operating conditions, and under multiple disturbances, we simulate the system and we store the data and we train the machine learning classifier. And that trained machine learning classifier is used together with the real-time data in the online implementation to predict the stability status and to initiate the preventive control actions. So this is what is this is simply what transient stability assessment with the help of artificial intelligence in power systems. So there are different algorithms which have been proposed in literature, so I will not go into details. There are different algorithms, and the most important thing is that we need to identify the correct input variables, because we are going to predict the stability status. That decision will it's very important decision. So we have to predict it fast enough. So we have to determine what are the input variables which carry useful information or useful features to your machine learning or AI algorithm. So that's the most important thing. There are different methods that have been tested, and some of these algorithms are in actual implementation also. Now, when it comes to oscillatory stability assessment with the help of artificial intelligence, in this case, as I told, what is required is to estimate the damping, and thereby we can initiate the required corrective actions. In this case, what are the possible control actions? It may be triggering of a damping controller or fax-based controller or any other relevant control measures to improve the oscillatory stability status of the power system. Now let's come to an important part, whether are we ready from Sri Lankan power systems point of view to apply artificial intelligence into the stability assessment. So from my point of view, now what we require is now for the fast prediction. Now this is the Sri Lankan map as per long-term generation expansion plan 2025 to 2044. Which shows us what are the existing power plants and the committed power plants. So to this network, let's say we're going to apply an AI-based transient stability prediction. So what we need is we need to measure it faster, and then we have to understand the upcoming situation as early as possible, and then predict the situation and act well before the system collapses. So to do this one in our network, from my point of view, what we need. So we must have a good data source. We must have a measurement technique which provides data fast enough with adequate dynamic features. So as per the existing technology in the world, that's coming out of a synchrophaser-based wide area measurement technology. And we have to have high-speed communication because those data should come to the center at a faster rate. I hope that's not an issue with the fiber network we have. Then we have to go for an integrated data platform. And other concern that I see is the dynamic system models, because we know that when we even do system studies, we try to adjust the dynamic data such that the simulation response matches with the measured response, and we go ahead with that model. However, we have to have correctly validated dynamic data set because we want to simulate the entire power system to generate the data to train the machine learning classifier, and then we can do the rest of the things. So this comes to the final stage of my inaugural lecture. So what I have contributed in this aspect. So first, now these are my contributions in the rotor angle stability assessment, which I did in my doctoral studies. So the first one is that we developed a new sophisticated a non-linear based approach to predict the stability status rather than waiting till the time domain trajectories converge. So that's one contribution. And then we also did, now when it comes to oscillatory stability assessment, we have to identify the dominant oscillatory modes. So through this algorithm, you can capture what are the real modes present in the network and their frequencies and the damping ratios. And after that, I have contributed in different ways. So this work is to identify the coherent groups of generators subsequent to the disturbance with the help of real-time data. And then I have also contributed in different ways with my colleagues in reviewing the relevant aspects. And I have also worked in two C-grade groups to apply this synchrophaser data into power system stability monitoring and control. And this case is like now, even though the model-based analysis is complex, we have to do it to identify the possible oscillatory modes in a power system. So this case is for the Lakvijay power plant that we did this analysis by completely modeling the entire system in detail and identified the oscillatory interactions between the generators and what can happen subsequent to disturbances in that particular power plant. And also the same work has been extended to renewable rich power systems. And this kind of an analysis is very important because if the system is going to be unstable in terms of oscillations, or if it does not have enough damping, we have to trigger damping controllers. So you can see that we can identify with respect to the change of the parameters, controller parameters, how the critical modes are varying, and we can then decide on the controller tuning as well. So in addition to that, now in these days, now we do all these analysis in simulation and we have to apply those things in real time. So with the available facility in the department that we do have these real-time digital simulators, and I have done a number of studies to implement these algorithms in real time on processors and validate their performances. For example, in the first one, so this case, what we did here was that we have represented the entire power system in the simulation software, and then we implemented those things and we showed the performance of the algorithms, because when you have a real-time network, it can experience any communication delays, many things. So with the help of this technology, we can check how robust our algorithms to these kind of changes in the network. So those are few contributions on my side in this domain. And here I come to the final stage. So now this swing equation is representing the behavior of the synchronous generators in dynamic conditions. And that's the real physics that we have. Even though we try to apply artificial intelligence into this particular problem, we have to do it with lots of care, because based on this algorithm, what we are going to predict is stability status of the power system. It's a very crucial decision. So we have to do it with so many care, and that's the message that I want to give at the end. So that concludes my presentation. And before winding up, I take this opportunity to thank everyone who were behind me to come to this destination. So thank you very much. And that concludes my inaugural lecture.
Thank you very much, sir. As expected, it was enlightening and it was very rich. And I could see the professor has put a lot of effort into it, and I believe everyone will take something home from that. Once again, thank you very much, sir. We are very grateful for this lecture. To show our gratitude, it's a time to present the lecture momentum to the professor today. For that, now I invite Professor Lidula Idanagamarachi to the stage. And also Professor Prasad also to the stage to receive the lecture. With that, we are reaching the conclusion of the today's inaugural lecture series. Before concluding, we are very grateful for the sponsors of the inaugural lecture series. We have our event sponsor Cargill's Private Limited, and we have our print media sponsor Daily FT. We have our social media sponsor Sri Lankan Scientist. So we are very grateful for the generous support of our sponsors. Without them, some of these matters would not be feasible, so their support is always appreciated. And once again, a huge appreciation goes to Professor Prasad for that educational and very rich lecture series, for delivering that very interesting series lecture. And once again, we are very grateful for all the professors, lecturers, and undergraduates who are joining with us through Zoom also. With that, we are concluding the 45th inaugural lecture series, and we will be meeting you with the 46th inaugural lecture series. Until that, stay safe. Thank you very much.